Swayam Prabha. Digital India. Educated India.
Welcome back to the organ printing course. So in the earlier lectures, we have discussed about the requirement of bioink for biofabrication. There also we have discussed like the requirement for cross-linking of the hydrogels, like to prevent the flow of the or to arrest the flow of the bioink after deposition for further stabilization of the structure, to prevent the deformation, to prevent the collapse of the structure, solidifying of the for solidifying the structure. Cross-linking is very important, right? And there also we have discussed, we have also discussed like the different ways the cross-linking can be done, like either it can be physical cross-linking, it can be chemical cross-linking, or it also can be photo cross-linking, right? So all these have their own advantages and disadvantages. We'll discuss that in the probably in the later slides, but first let us understand what are the nature of this cross-linking. Like when it is physical cross-linking, there mostly we talk about non-chemical interactions, like where the uh, interaction of the polymers of the hydrogel material can happen due to physical, that can like entanglement of the molecular chains, maybe ionic interaction, maybe hydrogen bonding, hydrogen bridge, or hydrophobic interaction, because maybe the hydrophobic pockets they can interact with water. That kind of thing can be used or can be utilized for inducing cross-linking within a hydrogel, right? Suppose due to different factors, if we can alter the interaction, specifically the non-chemical interaction within a polymer, then we can introduce cross-linking, we can introduce gelation within the material. So this physical cross-linking again can be divided into different types, like either it can be ionic cross-linking. Ionic cross-linking typically where when the suppose the polymer chains, they interact with other with other entities, either chemical entities or thing by ionic means. That means like there can be an ionic interaction between the opposite charges, then suppose the cross-linking initiates. So because of that, that is ionic cross-linking. A typical example is a very popular example is alginate hydrogel, because alginate solution they have this, when they have alginate solution, if we introduce calcium ions to the alginate solution, then what will happen, this calcium ion can bind to the uh, material, and due to this the alginate gel will be formed. So that this ionic cross linking actually helps in uh, forming hydrogel of this different forming gels of these different hydrogel aqueous or different hydrogels due to this ionic interaction. Similarly, stereo complex cross-linking is when suppose the due to the stereo reactions, the two different types of material, like suppose the hydrophilic and hydrophobic groups, if when they interact with each other and then they produce this interaction in certain way, so the cross-linking initiate, that can be another way to introduce cross-linking within a hydrogel. Other thing is thermal cross-linking. So due to this, based on the thermal reactions, right, like thermal induced changes, like because there are different various types of hydrogels, they are sensitive to the temperature, right? Because as different temperatures they behave differently. Their nature is nature, physical nature is different. Like suppose one example, typical example is the gelatin at less than 30 to less than 30 degrees centigrade. So that is a transition temperature. Suppose less than 30 degrees centigrade, the gelatin behaves like a solid gel material, but above 30 degrees centigrade it behaves like a liquid material. So this is a thermoreversible material where it responds to temperature, and below 30 it behaves like a gel. So that because of this physical interaction, physical cross-linking, the gelatin becomes gel below 30 to 30 degrees centigrade. So that's a typical example of thermal. Other than this is a other thing is collagen is a thermosensitive material, but it is a irreversible thermosensitive. Thermal cross-linking can happen if we incubate the collagen solution at 30 degrees 70 degrees centigrade, because the collagen it starts self-assembling. Because of the self-assembly nature, that induces physical cross-linking, and due to that that collagen will become gel. So these are all different physical type of physical cross-linking that can be very well utilized for bioprinting. And if you see in literature, you will find different. There are many examples of this thermal physical cross-linking. Similarly, the chemical cross-linking is another way to introduce gelatin within hydrogel, but here it is the chemical interaction. So there the chemical bond formation, covalent bond formation between the groups happen in case of chemical cross-linking. When two, suppose we introduce certain cross-linkers that will go and bind to the opposite through the go and bind two different groups of, suppose it can be it can be intermolecular, it can be intra chain polymer chain. So all these things can lead to chemical cross-linking. Chemical cross-linking is very powerful way to introduce cross-linking, because chemical cross-linking is also it is irreversible. Mostly physical cross-linkings are reversible in nature, but chemical cross-linking is irreversible. It is the permanent bond formation between the groups. Right? Similarly, there is another way to is the photo cross-linking. Photo cross-linking is when we use photopolymers, because the nature of the molecule, nature of the material is they are sensitive to light. Because if we expose them to light, the polymerization will start happening, and due to the polymerization the chains will get longer and longer, and the viscosity increases, and again they will become like a gel after the whole polymerization process, photopolymerization process. So photo cross linking happens because of this photopolymerization of this thing. And there we use different photoinitiators, like the different photoinitiators also we use there to initiate the photo cross linking process. So there are different different materials, like the examples are like gelatin methacrylate, polyethylene glycol diacrylate, and various other materials. Those are photosensitive, or those can be photo cross linked with the help of light. So these are the different mechanisms, cross-linking mechanisms for hydrogel. Now we'll discuss what are the advantage and disadvantages of each of these cross-linking mechanisms. Like for physical cross-linking, because this is a reversible in nature, interaction ensures constant viscosity during printing, because we can control the interaction of these materials, and we can actually physically, because of this reversible nature interaction, so here we can actually control the photo cross-linking, sorry, control the cross-linking, physical cross-linking of this thing. So it is actually one, here we have more control over the viscosity during the printing. And this system, this physical cross-linking system, is highly biocompatible with biological system, because there no chemical reaction is involved. It's mostly physical in nature. That's why this is highly is excellent compatible with the biological system, and mostly for it can be very well used for different bioprinting applications. The other this thing is, when we use physical cross-linking, there's a rapid assembly to gel after printing. Like one example is ionic interaction, because ionic interaction is very fast, so it can happen within a fraction of a second. So because of that, it is the shape retention or printing fidelity is very good, because the structure doesn't have get time to collapse before even actually the the structure started collapsing or deforming, the cross-linking happened, the physical cross-linking happened. Due to this, the gel form very fast. Other than this thing, suppose shear induced gelatin also another thing. Because of the shear, when we apply high shear rate, that time also the material, the viscosity comes down, so the material will come. But again, when the shear is removed, shear force is removed, then the material go back, the viscosity of the material will be very high, right? So that kind of shear induced gelatin also can be very well used for physical cross linking, and it is, that's why they are very they have a lot of advantages to be used for bioprinting. But they also have certain disadvantages, because of this reversible interaction, this the physically cross-linked hydrogels are not very stable, right? To improve their stability, sometime additional cross-linking agent can be required, right? So maybe we need to use additional cross-linking agent, or may we need to also use, it may post-processing cross-linking. Like suppose once the physical cross-linking is done, to improve the stability, we need to use certain secondary cross-linking or certain additional cross-linking is required. There can be instances where physically cross-linked hydrogels are mechanically weak, so that again, just to improve the mechanical property also, maybe we need to use certain cross-linking, certain other secondary cross-linking agent can be used, need to be used for this thing, because they are the structures are mechanically weak. Other than this, in certain cases there can be relatively slow gelatin. Mostly if it is based on, if it is not ionic ionic interaction, it is based on other than this, then the gelatin process can be relatively slow. So that is another disadvantage of this process. But and other thing is relatively high viscosity of the building blocks, because physical, if we are using physical means for cross linking, during the process, if the cross linking happens or the gelatin happen, then we end up getting very high viscous building blocks. So that is another, that can be another challenging to come up with the whole structure. So that we need to take care of this thing. So the physical cross linking, these are the advantages and disadvantages of this physical cross linking. Similarly, for chemical cross linking also there are certain advantages and disadvantages. Most the the most advantageous point of this chemical cross-linking is it allows post-processing cross-linking of mechanically weak physically cross-linked hydrogel. Here, as we have seen, that in physical cross-linking, first we can get the structure where we can get the gel very fast, but they are not mechanically weak, and the stability is also not that great. So we can introduce there some chemical cross-linking, so that the structure after printing, once the structure got gel because of this physical cross-linking, then there itself we can introduce some chemical cross-linking, so that the structure again gets stabilized, and further the mechanical property of the structure can be improved, right? And once the structure is chemically cross-linked, there is no further need for further irradiation or other further stabilization, and we can get mechanically stable construct after chemical cross-linking. So that's the advantage of chemical cross-linking. So suppose we are using high viscous material, high viscous hydrogel. So after printing, due to the high viscosity, the structure will be retained, or the printing fidelity is good. There we can do some chemical cross-linking, so that the structure again further stabilize, and the structure mechanical property also improves further. So that is the advantage of this thing, chemical cross-linking. It improves the structure, it improves the stabilization, structure stability, and also the mechanical property. Disadvantages, because the chemical cross-linking is we need to use certain harmful chemical cross-linking agent, right? So this some chemical cross-linking agents are very harmful, so that is that disadvantage. And but we need to use certain cross-linkers, those are less harmful, or those doesn't have any harm, those are safe to be used, okay? But the other thing is, it may this a trigger for chemical reactivity with required stringent control of cross-linking kinetics is needed, because for chemical cross-linking it is the thing that the process can be slow, it may take, the cross-linking duration can be longer, so it may take some time to cross-linking. So now how to initiate this chemical cross-linking, how to, so what is the trigger, how we can actually initiate, when to start the chemical cross-linking. So that is very tricky, right? Because most of what happens in bioprinting, what we do for chemical cross-linking, most of the time the chemical cross-linkers, everything is added in the within the system or within the biowing. Then actually the bioprinting process is done. Now after bioprinting, slowly the chemical reaction starts, and then the start structure getting stabilized or cross-linked. So how to trigger, to control the reactivity, chemical reactivity of this cross-linking kinetics, or the kinetics of this thing, that is a tricky thing. In case of photo cross-linking, there are certain advantages and disadvantages also, because this photo cross-linking, as I already mentioned, this is based on photopolymerization. Okay, so the photopolymerization through irradiation during printing does not affect viscosity during printing in the nozzle, right? Right. So what happens in certain cases, the photo cross-linking can initiate during the flow of the biowing through the nozzle, right? That time itself, the photopolymerization process can get started. But what happens this photopolymerization process, it, the viscosity of the material does not increase immediately. Okay, the viscosity, maybe at the beginning the viscosity doesn't affect much, so that it may not, it may help in it may help in the biofabrication bioprinting process. That can be advantageous, because we suppose we initiate the photo cross-linking process during printing, so the viscosity will can be increased little bit, but that may help in that may help in the printing fidelity. The printing fidelity can be improved further, or the structure can get stabilized after that, after printing. So that when the printing completes this thing, that time the so the photo cross linking has the advantage of being using in for during in situ bioprinting. During printing, the process can be utilized. Other thing is, it also allows for photo processing cross linking for the stabilizing of weak mechanically, weak physical cross linked hydrogel constructs. Because as we have seen, in case of physical cross-linking, we have seen that the structure, what is the structure we got, that is after printing, the structure is not that, the maybe that is not mechanically very strong, or structure is stable. So to improve the mechanical property or the structure stability, we can use this post processing photo cross linking can be utilized. So that is can be another advantage. But the disadvantage is high reaction rates necessary, as polymerization needs to be completed between nozzle and deposition. Because the interesting thing is, in bioprinting, your the photo cross linking should happen as the material started extruding. At that time, the cross linking should initiate, but the cross linking should complete before the material get deposited within the structure. Then only the structure relation can be maintained. So that's the requirement. That's what, because of this requirement, a very high reaction rate is required. So that can cause that can be cytotoxic to the cells, because the during this high reaction rate, the free radical can be generated within the system. Then that can cause cell damage. So, and for photo cross linking, often UV lasers are used, so that may involve exposure to the construct to irradiation, right? So that is another thing. So, but nowadays there are some visible light cross linking mechanisms available, so that can be very well used without exposing the light to the UV exposure. Right? Again, irradiation may affect the embedded cells. That can also happen. The embedded cells within the structure, they can also get the exposure, they can get exposed to the UV radiation, and then that can because of this UV radiation, the cells can get damaged. Right? So we need to take care of these things. But these are the advantage and disadvantage of photo cross linking. Now, depending upon your requirement, you can use either physical, chemical, or photo cross linking. Also, because it is mostly the time duration of this all this cross linking, it depends what type of because in certain cases, suppose your bioprinting approaches, your the cross linking needs to be very fast. Then you have to go for, you have to select a cross linking where you can get the very fast cross linking. Suppose ionic cross linking is very fast. So if your system allows ionic interaction, to be introduced, then you can go for that. Suppose in your bioprinting, your the material viscosity of is such that it prevents the collapsing of the structure. So the suppose it has a very high viscous, so structurally it can retain its shape after printing. So there you can introduce a cross-linking, that is probably through cross-linking, like chemical cross-linking. When it post printing, the cross-linking can you can introduce, and that can lead to a structurally stable, mechanically strong construct. Right? So depending on the requirement, you can choose any of this cross-linking. Other things, that depending on the chemical nature of the material, you can also choose different type of cross-linking mechanism. Because all these different materials, they have their own chemical groups or chemical moieties. So all these, depending upon that, also you can choose any particular type of cross-linking. So thank you all of you for attending this lecture. So again, we'll meet in the next lecture. Thank you very much.